Hello students, hope you are doing well. Dr. Melaku is here and today we'll see about the improper integrals. So last class we have seen about the definite integrals and it was defined as the definite integral is simply written as the integration from A to B f of x dx. So in case of the definite integral, we have said that this f, the integrand, is defined. Yes, if you remember, it is defined on a finite interval, yeah? Finite interval. You see, this AB is simply finite interval. That's why we have the lower and upper limits of integration. And secondly, we have said that f does not have an infinite discontinuity. F does not have an infinite discontinuity. Okay, so if f is defined in this way, which means we can integrate the integration f of x dx simply as equal to what? Equal to its antiderivative f of x, which is evaluated at b minus f at a. That was the fundamental theorem of calculus 1 to me. Now, when we come to the improper integral, this is simply to mean proper, yeah? That is proper. That's why it is called proper. Now, we are going to extend the concept of this definite integral into improper integral. So when we say improper integral, improper means not proper. Yeah? So when we say this improper integral, which means we can define the integration on a certain interval, which is infinite interval. It could be like this, for example, a up to infinity, f of x dx. Or it could be the integration from minus infinity to a certain number a, which is f of x dx. Or it could be of integration of this from minus infinity to infinity f of x dx. So in this case, f is what? F is defined on interval which is infinite interval. You can say finite interval. You see, which means the interval what we have here is simply a up to positive infinity, and this one is from minus infinity up to a, and this one is, you can see it from minus infinity to infinity. So these are infinite intervals. Okay, these are infinite intervals, as you can see it here. Whereas in the definite integral that we have already seen in last class, this definite integral, you see, always the function f must be defined on a finite interval. Maybe these are like a and b are like numbers to me. Or f does not have an infinite discontinuity. So whereas if we come to improper integral, always the integrand function or f could be defined on an interval which are infinite interval, one case. And second case, f could have what? Has an infinite discontinuity, okay? Discontinuity in the interval AB, okay? In the interval AB, okay? For example, I may give you like this. If I say the integration from, let's see, from 2 up to 5, 1 over, yeah, square root of x minus 2 dx. You see? So this is not definite integral. Because like at 2, when x is 2, the function is discontinuous. And it is not a single point, or it is not an finite number of discontinuity, but it is like x equal to 0 is vertical asymptote to me. Okay, so if it is vertical asymptote, you can imagine that we have infinitely many points, yeah, infinitely many points. That's why if f has an infinite discontinuity, the integration from certain point from a to b, where we have like an infinite discontinuity, is also treated as improper integral. Another example I may give you like this. The integration of from 0 to 1. You see, ln x dx. You see, ln x is not defined at 0, yeah? Ln x is not defined at 0. So you have to understand that this is also an example of improper integrals again. So what about this? Again, this is the next example is like the common errors that usually students commit. If, for example, if I make it this x minus 1, and if I define this integration from 0 up to 4, you see? So usually students perceive that this is definite integral, but not, you see? This integral is defined from 0 up to 4, which means we have numbers 0.1, infinitely many numbers are here, including 1, 2, and 3. But if you see at x equal to 1, the integrand function 1 over x minus 1 is not defined, which means we have x equal to 1 vertical asymptote. Okay, so for this reason, this is also improper integral. So improper integral will consider of these two cases where we have infinite interval and f has an infinite discontinuity in its interval. So these are the 2 points that we are going to consider for this case to me. So if we say that we have two types of just improper integrals, the first one is when we have like intervals which are infinite, yeah. So if you encounter to evaluate the improper integrals where the function f is defined on infinite interval, you have to use this method to mean. These are simple concepts. So it says if the integration from a to t f of x dx exists for every t greater than or equal to 0, then the improper integral from a to b, which is defined on a unbounded interval, yeah? You can say from a up to infinity, where this is infinite interval, yeah? Is simply how to evaluate. This is a technique. The integration from a to infinity f of x dx is you have to apply limit, okay? So you have to apply limit, and instead of infinity, you have to replace by some variable, let's say t for common understanding now, and t must be approaching to infinity of f of x dx. So you will treat this as the normal integration that you know. Also, it may need some techniques of integration that we have seen in class 2. Then after you obtain the integration, then it will be in terms of a and t. Then finally, you have to apply limit as t goes to infinity to mean. So if the limit exists, we say that the improper integral converges, okay? I will explain it later on. And similarly, if the improper integral is of this type, you see the integration from b to minus infinity. So this will have like from minus infinity, this is open, up to b. You see, this is also infinite interval. Then the integration from minus infinity b f of x dx is the same. You have to apply limit where the infinity is replaced by t and t is approached to minus infinity of f of x dx, provided that this limit exists as a finite number. And the last case is what? If the integration, like the integration from a to infinity f of x dx and from minus infinity to a f of x dx are convergent. Just when we say convergent, the limit exists, okay? Limit exists, or it goes to just like a number in the set of real number. Then we define, you see, the infinite interval is now from minus infinity to infinity f of x dx, you can have just like you can divide because we have infinity is like this in the number line. So if you take any point, arbitrary point A in between them, then you can divide the integration into the integration from minus infinity up to A f of x dx plus the integration from A up to infinity f of x dx, which means you can apply the two methods that we have in it in here, then adding them, you'll obtain a number to me. So the improper integral said to be they are convergent if the corresponding limit exists, okay? Which means as I have explained here. Otherwise, we can say that the improper integral diverges or they are divergent if the limit does not exist, okay? So when we say improper integral, you see, always we have to talk about divergent or divergence or convergence to me. Convergence. Why? Because improper integrals are about the limits, yeah? Limits. So when we say limits of a certain function, if you remember in chapter 3, does the limit exists or does not exist, yeah? So if it exists, we say that the limit converges to a certain number. Otherwise, we say that it is divergent to me. Okay, let's see some examples on improper integral. Suppose you encounter to solve this improper integral, okay? The integral is simply from 1 up to infinity of 1 over x squared to dx. So how are you going to find it? So first of all, you have to understand that this is improper because we have infinite interval to mean, yeah? This is the infinite interval what we have. Therefore, in order to do this, we have said that you have to apply limit, okay? Limit of the integration from 1 up to t. Instead of infinity, I use t, then 1 over x squared dx. Then I have to apply limit t as goes to infinity. Finished. So, but the integration of 1 over x squared is simple, yeah? Can you remember? The integration, you can take it off like this. Remember that the integration of 1 over x squared is dx is simply, you can say the integration of x minus 2 dx. So just plus 1, this will be x to the power of minus 2 plus 1 over minus 2 plus 1, which is x to the power of minus 1 over minus 1. So this is minus 1 over x. This is easier. Therefore, this is the same as the limit of. So instead of 1 over x squared, I have to use what? 1 over x negative. And I have to evaluate this at upper and lower limits of integration, and t must be approaching to infinity. Now, this is the same as what? Evaluate. The limit is simply minus 1 over t minus of 1 over 1. Yes, t goes to infinity. And this is the same as the limit of minus 1 over t plus 1. True. But as t goes to infinity, what will be minus 1 over t? That will be 0, yeah? So this is 0 plus 1. This is 1, which means we can say that the improper integration from 1 up to infinity of 1 over x squared dx is equal to 1, which means it is convergent. It converges to 1 because the limit exists, yeah? Converges to 1. So what we are doing, let's interpret graphically, okay? If the question was like this, for example, if the question was to find the integration from 1 up to 5, 1 over x squared dx, just this is simple definite integral, yeah? The definite integral would be what? The same as the integration of 1 over x squared is minus 1 over x then evaluating at 1 and 5, we will obtain 4 over 5 like this. You see? So this is simply what? The area of the region, just if you remember in the application of definite integral, I have told you that it is the area of the region under the curve 1 over x squared, which means this one. If you see this one, it is the integration from 1 up to 5, okay? Which means we have finite interval. This is the finite interval, you see? So this is not improper integral to me. Whereas if you see the upper figure, let me say it A and B, you see, it is defined on an infinite interval. It starts at 1, that it goes to infinity, you see? So this is going, it is increasing and increasing, but it never touches the x-axis to me. That's why it is infinity. And that's why it is like the improper integral. So this is the integration from 1 up to infinity f of x dx, which is 1 over x squared dx. Whereas the second one, this one, b, is what? It is simply the integration from 1 up to 5, 1 over x squared dx. So this is definite integral. Okay? Whereas this one is improper integral. Hope you understand their difference and the technique how we are going to manipulate to me. Okay, please do this as your exercise. Okay, for it is simple because they are the same. Yeah, exercise for you. Just to give a hint, it is simply the integration of 1 over x dx is simply what? Because it is improper, you have to apply the limit of the integration of 1 over x from 1 up to t as t goes to infinity. And get the answer, okay? If you find the integration is divergent, you are correct, okay? Divergent. Check that it is divergent, okay? It's simple. So just I want to focus on another important point or another important example. What if you face to solve a question from minus infinity to infinity, which is an improper integral because it is defined on an infinite interval? How are you going to evaluate? This is the point. So solution, just as I told you, first you have to take any point between them. This is minus infinity, this one is infinity. So just A. What is A? If you take A is equal to 0, just it will make symmetric and it will be good for calculation. Otherwise, you can also use any other number. Maybe you can choose 1, you can choose 5 and something like that. Don't worry about that, okay? Now for simplicity, I will divide this from minus infinity to infinity of 1 over 1 plus x squared dx as what? As the integration from minus infinity 0, 1 over 1 plus x squared dx plus the integration from 0 to infinity 1 over 1 plus x squared dx. So both this and this are what? They are still improper, which means we have to apply improper integral or limit on both sides, on the first one as well as on the second one. So just I will focus on the first one, this one, A part, and B part will be your exercise, okay? You can do it by yourself because we have done similar examples that ranges from some number to infinity, but we didn't do from minus infinity to 0. Now let's solve one by one, okay? So solution A, the integration from minus infinity to 0, 1 over 1 plus x squared dx, you have to say what? It is the limit of the integration from t to 0, 1 over 1 plus x squared dx as t goes to what? Minus infinity, because this is minus infinity. Now, what is the integration of 1 over 1 plus x squared? Do you remember the antiderivative of the 1 over 1 plus x squared? I think everybody must know this. And the integration of 1 over 1 plus x squared is simply the tan inverse, yeah? The arctan function, tan inverse of x. So t must be goes to minus infinity. But I should evaluate tan inverse on what? On t as well as 0 to mean. Yes? So this is like the limit that I have to apply. And this is the same as the limit of as t goes to infinity minus infinity. I have to check tan inverse of 0 minus tan inverse of t. Okay? This is my point. So let me come back here. But what is tan inverse of 0? I hope this is simple. It is elementary concept. As t goes to minus infinity, tan inverse of 0 is 0. Yes? Minus, just I have to say what? Tan inverse of t. So this is simply what? It is minus of the limit of tan inverse of t as t goes to minus infinity, okay? So what is the limit of tan inverse of t? That is the point. So this is also simple concept. We have minus here. So the tan inverse, the limit of tan inverse of t as t goes to infinity is minus infinity is minus pi over 2. Okay? Which means minus of minus pi over 2 is pi over 2. Just to answer this question, if you are good on limit, what is the limit of tan t? You can make it like this. Or tan x, as x goes to minus pi over 2. So if you know this one, just finding the limit of tan inverse of t as t goes to minus infinity will be so easy to me, okay? So this is minus infinity. Just you can check it. That's why I'm saying that tan inverse of t as t goes to minus infinity is pi over 2. Therefore, we can say that the improper integration from minus pi 0, 1 over 1 plus x squared is pi over 2. Wow. So it converges, yeah? Converges. So one part is done. Next, you have to do this by yourself, okay? The second part. And they are similar, okay? Just check. Check. Just they are the same by the same procedure because integration of 1 over 1 plus t squared x squared is the same tan inverse of x. And similarly, the integration from this 1 over 1 plus x squared dx is also pi over 2. Okay? Both of them are pi over 2. So what will be the overall integration? That is from minus infinity to infinity. That will be the sum, yeah? Therefore, the integration from minus infinity to infinity of 1 over 1 plus x squared dx is pi over 2 plus pi over 2, which is pi. Converges. Okay? Converges. So what we are saying is, this part alone is what? The integration from 0 to infinity, 1 over 1 plus x squared dx. And this part is the integration from minus infinity to 0, 1 over 1 plus x squared. So this half part is pi over 2. This half part is pi over 2. And the whole is what? Pi. So you see why it is improper? Because like the infinity is going this way, yeah? The graph will continue like this without touching the x-axis. Okay? Without touching the x-axis. And the graph you see is like 1 over 1 plus x squared. Just check this by derivative, okay? Graph this, graph it. It will be good for you as exercise of on the graph of rational function. Graph it, okay? By derivative concept. So this is what improper integration, which means this one is convergent to me, yeah? What if one of the improper integration is divergent, which means the whole integration will be divergent and no need of checking the other to me. Okay, great. So this is the first part of improper integration where we consider the unbounded intervals. Okay. So the second phase will follow after few minutes. All the best.